Hello everyone. Welcome to the SWAYAM NPTEL course on Mathematical Geophysics. We start the final module number 8. This is the data-driven analysis in geophysics. This is the first lecture of this module, Fourier analysis and transform. In this lecture, we would be covering the concepts related to Fourier analysis and Fourier transform. This lecture is composed of 5 components. First, we will look into the basic Fourier transform theory. Second, Fourier integral theorem. Third, the similarity and shifting properties of Fourier transform. Fourth, we will be looking into the derivatives and integration of functions and their Fourier transforms. Finally, we would look into the applications of Fourier transform in geophysical studies. So let us begin. The Fourier transform theory. The Fourier transform theory is very important aspect of geophysical data analysis. In geophysics, the data is measured using various geophysical instruments over space and time. Analyzing this data is of utmost importance to interpret the subsurface properties and other understanding of various geophysical phenomena. Analyzing the measurements which are in the form of time series data is extremely important to be performed, and further understanding of geophysical processes can only be obtained through a proper analysis of these data. Now, Fourier analysis and techniques have proved to be very useful in analyzing data sets in all domains of science and technology. The Fourier series and Fourier transform comprise of the two components of Fourier analysis. First, we would look into the Fourier series. The Fourier series is a method to represent a function in terms of sines and cosines. We have seen such representation in the spherical harmonic studies in previous lectures. Now we focus on the Fourier series part. Let us consider x of t as a function of time. This function of time can be represented in terms of Fourier components as given here. X of t is summation over n equals 0 to capital N of all the components which are given by the Fourier components e to the power 2 pi I fn t. This is the complex Fourier exponential term. Its amplitude is given by xn or Fourier series components. Xn are constant coefficients and Fn is the frequency. Now, since x of t is any arbitrary time series function, the Fourier series is capable of representing various geophysical signals in this way. One typical example is that of tides, which occur in ocean. These tides represent displacement of water above the sea level, which can be very appropriately represented in terms of Fourier series. Also, these Fourier series are known as harmonic development of a function. Next, we come to the Fourier transform. The Fourier transform is a method of representing the function in a continuous frequency domain. Note that the frequency components of Fourier series Fn are discrete. Whereas the frequency component of the Fourier transform are continuous. What does this mean? It means that Fourier series utilizes discrete frequencies such as 1, 2, 3 or zero point 0.1, zero point 0.2, zero point 0.3 as discrete values to represent a function, while Fourier transform utilizes a continuous change in the frequency, which is over infinitesimal changes of frequency values to represent a given function. Thus, the same function x of t is represented as an integral instead of a summation. X of t can be represented as an integral over the entire domain minus infinity to plus infinity e to the power 2 pi I f t, where f is the frequency, which is a continuous variable. X tilde of f is the coefficient function. Thus, the major difference between Fourier transform and Fourier series is that Fourier transform can represent any arbitrary function, while Fourier series cannot represent an arbitrary function. Functions which are amenable to accurate Fourier series expansion are periodic functions over an infinite domain. Now, Fourier transform can also represent non-periodic functions because of its continuous frequency range. The expression x of t equals integral plus minus infinity and so on, as given in equation number 2, is known as the inverse Fourier transform. Now, this integral holds only and only if x tilde f can be written as integral over the entire domain of time x of t into e to the power minus 2 pi I f t. This is known as the forward Fourier transform. Now, these are the two parts of the Fourier transform. These two equations define the function x of tilde f, which is the Fourier transform of the time function x of t. This can be written as capital F of x of t equals x tilde f. F is the cyclic frequency. Equation 2 and 3 represent combinedly the Fourier transform pair. Now, let us have a look at the Fourier transform in the radial frequency domain. The radian frequency domain is given by the radian frequency omega, also known as the angular frequency, which is 2 pi into cyclic frequency. The inverse and the forward Fourier transform are represented here. Next, we look into the Fourier integral theorem. Now, the Fourier integral theorem is a set of 4 theorems. It defines how and when the Fourier transform exists and what is its behavior. The first theorem is the Dirichlet condition theorem. Now, before we move on to the statements of this theorem, let us have a look at the adjacent diagram for notational and geometrical understanding. This diagram is a function of time represented over a domain minus pi to plus pi. We can see various features of this function. This function is continuous over certain regions and discontinuous at finite number of places. For example, these are the places where this function is discontinuous, and they are 8 in number. This is the finite number of discontinuities of the function. In between these discontinuities, the function is continuous, such as this region. So this function can be treated as partly continuous and partly discrete with finite number of discontinuities. Thus, such a function can be represented by x of t, which is periodic over a domain minus pi to plus pi, which means any 2 pi periodic domain which is beyond this, such as pi to 3 pi, 3 pi to 5 pi, etc., will be same as this part of the function shown. Thus, this is a 2 pi periodic function. Thus, having this 2 pi periodic function and having finite number of discontinuities, with finite number of maxima and minima values, such that all the points in the domain are single valued, we can look into the Dirichlet condition. Note that the number of maxima and minima are finite. These are the location of maxima and minima, which are finite in number. One additional condition which is required is the modulus of x of t dt is finite over integral over the entire domain, which means it is absolutely integrable. If all these conditions are satisfied, then the Fourier series converges to the function x of t at all points in the domain where the function is continuous, and at the jump or discontinuities, the Fourier series converges to the midpoint of the jump. For example, at this point where the function is discontinuous, it has two values for this location. For the location shown by the small dot, the cross given in 2 in number represent the two values which are present at this discontinuity. Now, the midpoint value is shown by the larger circle dot. This would be the value where the Fourier series would converge to if all these conditions are satisfied. That is the Dirichlet condition theorem for Fourier integral. Now we have the next Fourier integral theorem. The conditions for the Fourier integral theorem is that it satisfies the Dirichlet condition over every finite interval, and the x of t function is absolutely integrable. Then the Fourier transform given by equation 2 and 3 in the previous slide holds and is accurate, which means that for the forward and inverse Fourier transform to hold, we need the function x of t satisfy Dirichlet condition, and it is absolutely integrable over the domain. Next, we have the Fourier sine transform. Now, Fourier sine transform relates to only the sine part of the Fourier series. It is very useful to represent odd functions more effectively. Since sine is an odd function, the representation of odd function requires only the sine part, and the cosine part represents the even functions. Thus, Fourier sine and cosine transforms are complementary. Now x subscript s t is the time dependent function, whereas its Fourier transform is given by x subscript x as a function of omega. Now the forward and the inverse transform are given as these quantities, where the exponential term in the integrand is replaced by sine term. Similarly, for the cosine transform, the cosine Fourier pair are given by x subscript c. Cosine transform pair, the integral term, has cos omega t instead of e to the power 2 pi f t. Now these are the Fourier sine and cosine transforms which are complementary to each other, and combinedly they represent the total Fourier transform. Now let us look at the similarity and shift properties of Fourier transform. These are very useful for geophysical applications. The similarity property. The similarity property refers to the scaling of the function in time and frequency domains. It describes how compressing or stretching a function in time domain affects its Fourier transform. Thus, we would be looking into functions in time domain which, when compressed, change accordingly in the Fourier domain. Now, let's say we have the function x of t. This is in the time domain. Now, this function is scaled by a factor alpha. Now, the function becomes x alpha t. How does this look in a graphical form? For example, let's say this is the function x of t. This is the expanded form. Now, x of 2t is the expanded version of the function x of t, while x of t by 2 is the compressed version of x of t. Here alpha is 2 and 1 by 2 respectively. This is scaling by a factor alpha. Now we will be looking at what will be the Fourier transform of these scaled functions. That is given by x of alpha t transforms to 1 by modulus of alpha x of omega by alpha. For example, if x of t transforms to x of omega, then x of 2t transforms to half of x tilde omega by 2. We have seen that if modulus of alpha is greater than 1, it indicates stretching. In frequency domain, it is compressing, because the factor by which omega is multiplied is less than 1. If alpha is less than 1, it indicates compressing in time domain and expansion in the frequency domain. From this, it can be understood that the effect of similarity, that is expansion or compression, is opposite in time and frequency domain. Next, we'll look at the shifting property. Now what is shifting? Shifting is depicted by the change in the location of the function. Suppose this is a function of time, then the shifting would indicate either this, which is shifting to the right, or this, which is shifting to the left. Shifting to the right is given by x t minus t naught, while shifting to the left is given by x t plus t naught. Here, the shifting property of a Fourier transform describes how the Fourier transform of a function relates or changes when a function is shifted. So we would be looking at the frequency representation of xt plus t naught and t minus t naught in terms of the shifting property. The shifting property allows various manipulations of the function without changing the fundamental shape. Now, mathematically, if the function is shifted by t naught, it is represented by x t minus t naught. If x transforms to x of tilde omega, then the shifted signal xt minus t naught transforms to x tilde omega multiplied by e to the power minus omega I t naught. Thus, shifting a signal in time domain induces a phase shift in the frequency domain. However, the magnitude of the frequency spectrum x of tilde omega stays the same. The phase changes by minus omega t naught. Thus, similarity and shifting properties of Fourier transform are very useful in geophysical datasets. The geophysical datasets are to be combined and processed using similarity and shifting properties for better representation and interpretation of the subsurface phenomena and geophysical aspects. Next, we look into the derivative and integration of Fourier transform. The derivative property of Fourier transform relates to the differentiation in the time domain to its effect in the Fourier transform domain. Now, if a function is differentiated in the time domain, in the frequency domain, it is pre-multiplied by a factor I omega to the power n, where n is the order of differentiation. Thus, differentiation in time domain is equivalent to multiplication in the frequency domain. This property is very useful in analyzing the rate of change of signals and enhancing specific features of the frequency spectrum. Next, we consider the integration of Fourier transforms. If xt is a signal and x of omega is its Fourier transform, then the integral of the time domain function leads to the Fourier transform given by 1 by I omega x omega plus 2 pi c delta omega. Now the first part is the division of x of omega by I omega. Just as the differentiation leads to multiplication in Fourier domain, similarly integration leads to the opposite effect of division in the Fourier domain. Thus, the original Fourier transform x tilde omega is divided by I omega. The integration constant which can arise due to the integration of the function in time domain is then also transformed into 2 pi c delta omega. 2 pi c delta omega is the Fourier transform of constant functions, and thus it appears as the Fourier transform when an integration of the function in time domain is considered. Here delta is the Dirac delta function. The Dirac delta function is infinity at omega equals to 0 and 0 when omega not equals to 0. Now we look into the various applications of Fourier series in geophysics. We have come across these applications in previous lectures in the context of spherical harmonics. However, we would reiterate them to emphasize the importance of Fourier series in geophysical systems. First, seismic wave analysis. The seismic wave analysis decomposes seismic signals into frequency components to identify body and surface waves. In seismic wave analysis, in the Fourier spectrum, the high frequency signals indicate shallow features, whereas low frequency components indicate deeper structures in the Earth's interior. Thus, representing a seismic signal in frequency domain helps to segregate deeper and shallow structures. In geophysical exploration, we have the gravity and magnetic survey methods. In these methods, Fourier transform separates the short wavelength and long wavelength features. The short wavelength features represent shallow structures, whereas longer wavelength features represent deeper subsurface structures. This helps in locating the depth of the anomalies, which are mineral deposits or other resources which are sought after using these geophysical methods. Also, Fourier transform can be used to project the data to higher or lower altitudes in gravity and magnetic surveys. This is in line with the upward and downward continuation phenomena which we have discussed in the context of potential theory. In the electromagnetic survey method of geophysical exploration, Fourier transform decomposes the electromagnetic signals or the variations of electromagnetic field to assess the frequency-dependent penetration of the signals. In these surveys, high-frequency map allows the identification of shallow features, while low-frequency detect deeper features. Thus, we come to the conclusion of the Fourier transform in the context of geophysical and general context. The Fourier transform is very vital for decomposing signals. It decomposes signals into sinusoidal components, which are categorized into various frequencies. Based on the frequency content, various physical interpretation can be found out, which is otherwise very difficult to obtain from the time-dependent function representation. The Fourier transform provides much deep insight into both time domain and frequency domain characteristics of geophysical data. The Fourier transform enables the construction of filtering techniques, which we will be discussing in further lectures. These filtering techniques help remove noise in seismic, gravity, and magnetic data. Removing noise enhances the interpretation and the quality of estimation and exploration of the subsurface. In natural phenomena context, Separation of short wavelength and long wavelength structures in gravity and seismic studies and magnetic studies is enabled through the use of Fourier transform methods. Thus, overall, it can be said that Fourier transform techniques is of very much importance in geophysical data analysis. Thus, data-driven analysis into geophysical data cannot be done without the use of Fourier transform. One can refer to the following references for more details of Fourier transform and Fourier series. Thank you.